Hello everyone, and today we're going to go over the example in lecture 15. So in lecture 14 we learned how to derive equation of motions for a single link or a single rigid body using Newton's second law and Euler's second law. So in this lecture we're going to see a complete 4-bar linkage. So we name the ground as number 1, input as number 2, coupler as number 3, and then the slider is number 4. So there are 4 links in it. So we know the geometry of all these links. So they are a rod with a radius of 0.1 meter. And then the slider basically is a big block. So it's 0.8 by 0.4 by 0.4 meter block, and then we know that all these materials are made of steel, so the density is about 8,000 kilograms per square meter. So we also know the length of each link. We know that the grounding link is flat, or actually here this has no meaning, you can just ignore it. The input angle is theta 2. Your theta 2 is right now is flat, but then at the same time is rotating counterclockwise in a constant speed of 0.4 pi radian per second. Okay, so we have seen these crank slider mechanism before. Actually, we have already completed the position analysis, velocity analysis, and acceleration analysis. So that's why we already know the orientation. If you don't recall, the orientation of theta 3, which is here. And then we already know the distance d from previous analysis. So my question is, if we put a motor here, if we have a motor attached to the joint O2, how much torque should the motor provide to drive the entire system at that position? So we need to find the T input. All right. So because that's system dynamics, we need to draw a free body diagram. So we actually have 4 different links. So the first link is the input link. Let's name it as link number 2. And then we have joint O2, joint A, and then there were 2 forces at joint A, which is F 3 2x, F 3 2y. So here I would like to explain the meaning of the subscript. So we have F, I, J, and K. I means where this force is from. J means where the force is applied to. And then K is the direction of the force. So which means it's either X or Y. So the K is either X or Y. It indicates your force is horizontal or vertical. So I and J means where your force is from and where is your force applied. For example, we have F32 here. That means your force is applied by link number 3 and is applied on link number 2. So if you look at your joint A, that actually makes sense. So this force is generated by this coupler link, which is number 3, and is applied on this number 2 link. So that's why we have F32 X and Y. So we also have 2 reaction forces at the joint O2. So think about it. What are the subscripts for these 2 vectors? So it should be F, the force is from the grounding link, which is number 1, is applied to the link number 2. So that's F1 2x, and then that's F1 2y. And then we know that the center of gravity, G2, is right in the center of this link because our link is uniform. Okay. Anything else? All right. So we're missing these input torque, T input, because there is a torque applied by the motor. So that's the so this is the free body diagram for link number 2. All right, so we can draw a similar free body diagram for link number 3. Let's start from a new slide, because you're gonna need a lot of space to derive the equations. So we have link number 3, and then the joint is A and B. The center of these link is G3. And then what are the forces here? So here we have reaction force at the joints. Okay, so what are these subscript here? So this is the force is applied to link number 3, but then on the joint A, the force is actually from link number 2, is along horizontal direction. Okay, the same way 2 to 3 along y direction. Same thing here. The force is applied by the slider, which is number 4, applied on number 3, horizontal, F4 3y vertical. So these subscripts are extremely important in your force analysis. If you mess up with this subscript, then you're going to have a wrong solution for sure. All right, so there's no torque applied to this because there's no motor attached to it. So that's link number 3. We also have the last link, which is a block, link number 4. So the block is sitting on a flat ground. It's sliding on the ground. We know that there is a supporting force N from the ground. If you don't want N, this grounding force is actually from number 1 applied to 4 and is only along the vertical direction. So you also have a force applied by link number 3. So that's F3 4 X and then F3 4 Y, right? And then the center of gravity, which is G4. Make sense? So up to this point, we draw 3 free body diagrams. Then we can derive for the equations. So if you go back to the example 1 and 2 in the lecture number 14, we already know the acceleration A2 at the center of this link. So your A2 actually have 2 components, A2x and A2y. Make sense? So we already know this acceleration from acceleration analysis. So then we can derive for equation of motion. So how many equations we have? We have 3. So one is along x direction, linear motion. So we have all the force along x. Oh, we have 3 2x plus F1 2x. That's going to generate the linear motion of the center of rotation. In this case, we assume the center of gravity, the center of rotation. So we have M2 A2x. In the same way, you can find the equation along y direction. So that is F3 2y plus F1 2y. So these two forces together is going to create the acceleration along y direction. So we also have rotation. So what torque we have? We have an input torque. This input torque is going counterclockwise, so that's why it's positive. We have the torque generated by force F12. We also have the torque generated by F32. Okay, so these 3 torques together is going to generate a acceleration. So this is the angular acceleration, and then the angular acceleration is theta 2 double dot. And then in this case, we know that the speed is constant, so the right hand side is actually 0. Okay, So we have three equations. We just need to find whatever we know. So T input is something we don't know. F32x, the reaction force. Those reaction forces are not known. So what else? So what is the T12 then? Your T12, by definition, is the position vector R12 cross product force 1, 2, right? So what is your R12? By definition, your R12 starts from center of rotation, and it should end at F12 force. Okay, so right now your F12 force is applied around joint O2, so that's why your R12 vector is actually G2O2 vector, right? Okay, so what is your G2O2? Your G2O2, by definition, let me use a red color. So these red color is going to be your R12 vector. How can we describe that? It's really hard to describe R12, but it's really easy to describe R21, right? Or I should use a different subscript. It's really easy to describe O2, G2, right? Because then we can use a complex number. We have O2 G2 minus equal to minus half of the length, and then EJ theta 2. Make sense? So what is our L2? Your L2 is link number A, is link A, so we eventually have minus half A EJ theta 2. So we want to write this R12 vector in Cartesian coordinate. So we need to find the real part. Your R12 equals to R12x, R12y, and 0. And then the x component, just the real part of this, is minus half A cosine theta 2 minus half A sine theta 2, and then that equal to 0. Okay, so that's how you find the position vector we need to use to calculate T12. So F12, we already know that. Your F12 is, let me write it in here, have two components, x components, y components, and z component, right? So by definition, we know that the torque is going to be minus R12y, sorry, it should be positive R12y F12x minus R12x times F12y. So that's the torque we're talking about. You can ignore the K component because we know that all these three torques are gonna be along the same direction. So you can ignore the direction vector K. So that's our T12. So we got these from the cross product definition. If you forget how we got there, you can go back to lecture number 14. Okay, so we have T12. So how about T32? We just follow the same rule. Your T32 is R32 vector cross product F12, sorry, cross product F32 vector, right? So we need to find R32 position vector. So again, this vector should start from the center of rotation, which is your G2, and then this vector should end at the point where your force 32 is applied. So that means R32 vector is actually G2 A vector, right? So where is your A vector? where is this vector? So you have your G2A vector. So this one is your R32 vector. Okay, so you can see that from the geometry relationship, you will note that your R32 vector is just minus R12, right? Because they have the same length, they're on the same line. The only difference, they have this different sign. So that's why you just put a negative sign in front. So by sum these together, we have, okay, I just figured out how to insert a new blank page after that, because this derivation is going to be super long. Okay, so we have our R32 vector. We know that is minus R12, right? So then we know your R32 vector equals to minus R12, and then your R12 is already given in the end of the first slide. So we have minus, sorry, 2 minus become positive. That's half A cosine theta 2, half A sine theta 2, 0. And then your F32 vector, again, it has 3 components. It's F32x, 32y, and then the z component is 0. So by calculating the cross product, the cross product is a determinant. You just lay out all these entities in the correct order. There's x-axis, y-axis, you have a z-axis. Eventually that gives us T32, and then you can easily copy and paste. It's half A cosine theta 2 F32y minus half A sine theta 2 F32x. To save some space, I'm going to keep it as R12 minus R12x F32y plus R12y F32x. Okay, just leave it as that. All right, so we have T32, and then what else we need? If theta 2 double dot is not 0, then we need to calculate J2. Your J2 is actually 1/12 m2 L2 square, and then it's 1/12 m2 a square, right? So m2 is the total length of the total mass of this link. So we know this is a rod. The rod has a diameter of 0.1 radius. So we know that the volume of the rod is pi times r squared times the total length, and then the total mass would be rho times v2, or rho pi r squared a. Okay, so that's all we have for this equation. Okay, one thing I forgot to mention. What is a2x and what is a2y? So by definition, in order to get the acceleration of point G2, we know the O2 is not moving. We know these theta, the information of this theta 2 angle. So by definition, in order to calculate a G2 vector, we need to find the O2 G2 position vector 1 in the beginning, and then calculate its time derivative twice. And then what is your O2 G2 vector? So this is half of the length EJ theta 2, right? Your length is a constant, but then your theta 2 is time varying. So we know that DOG2 dt, which is the velocity of your G2 point. That should give you j theta 2 single dot 2a e j theta 2, right? And then one more time derivative, we know the acceleration equals to j theta 2 double dot half a e j theta 2 minus theta 2 single dot square half a e j theta 2. So in this special case, we know that the acceleration is 0. So that's why the first term becomes 0. So we have the acceleration equal to minus theta 2 dot half a e j theta 2. And then that's the complete vector. But then according to the definition, we need to a2x, a2y. So that means your a2x is just the real part of your complex vector. So that is minus theta 2 dot square half a cosine theta 2. And then your a2y is going to be the imaginary part of this vector ag2. That is minus theta 2 dot square half a sine theta 2. All right. So up to these points, we know what a2x is, a2y is. We know the moment of inertia. We know the mass of the system. So that means on the right-hand side, everything is known. On the left-hand side, we don't know these reaction force and input torque. And then we don't know these torques, but then we can write these two torques as functions of reaction force. So eventually we have 1, 2, 3 equations, but 5 unknowns. So the system is underdetermined. So that's why we have to move on to find more equations. So here we have the link number 3. Again, you're going to know the A3 vector there, right? So that's actually the practice question number 1 from lecture number 14. You already know the reaction force on the edge on both ends, and then you want to find the equation of motions. Again, we have 3 equations, right? Along the x direction, we have f23x plus f43x. That's going to give us m3a3x. Along the y direction, we have f23y plus f343y equal to m3a3y. Okay, we'll have another rotation around G3. And then this gives us the torque, which is introduced by force 2-3 plus the torque introduced by force 4-3. That's going to generate a angular acceleration around G3. So the acceleration here, let me label it out. So the angle here is theta 3. So that's why we have theta 3 double dots. Again, your J3 is 1 over 12 m3, the length of the bar, which is b squared. Okay, m3 again, you can calculate from the density, the density and the volume. All right, so what is the T23 and T43? So T23, oops, by definition, your T23 is just R23 cross product F23, right? What is your R23? Your R23, again, that's the position vector for F23. So you need to start at center of rotation, which is G3, and it should end at where the force is applied. So your force is applied at point A. So that's why your R23 equals to G3A. That is your vector. Okay, let's use the red color. And then we already know that the theta 3 is here. So by definition, let me see, your G3A equals to half of the length times EJ orientation, right? So if you want to write R23 in Cartesian coordinates, you would have R23x, R23y, and 0, where your R23x is just the real part of this vector, that's 2b cosine theta 3. R23y is the 2b sine theta 3. Okay? And then you do cross product. If you don't want to do the calculation again, you can actually directly go back to these equation and then replace the subscript, right? So right now you have R12, F12, but then you just want, oh, I think I have a typo here. R12. So that should be positive. That should be minus. Okay, I just go back and fix the typo here. So I have the sign in the wrong order. So it doesn't matter. So, okay. So here, by definition, we know that your T23 is going to be R23 x F23 y minus R23 y F23x, right? So that means your torque can be written as function of forces. And then R23x, R23y, they're just position vectors, so they are already known. It's provided in here. So in the same way, you can find your T43, that is simply R43 vector cross product F43 vector. So again, you can write it as just copy and paste, because if you compare this equation with this one, the only difference is the order, is the subscript. 2,3 becomes 4,3. You can copy and paste R43x F43y minus R43y F43x. So you have the same format, but only thing different is the subscript. Okay. But where is R43? So again, your R43 is a position vector. It starts at center of rotation G3. It ends at where the F43 is applied. So it actually ends at point B. So that means in this case, you have your R43, right? And then the red vector is your R23. So from the geometry relationship, we know that R43 vector is minus R23, right? So that means your R43x is just minus R23x. R43y is just minus R23y. Then you can do the calculation. Okay? So up to this point, let's find all the unknowns in the equation. We don't know the reaction force. The T23, they are unknown, but then your T23 can be written as these unknown forces. Okay? All the things on the right-hand side, they're already known. So here, the total mass, the acceleration, and angular acceleration, moment of inertia, that all can be calculated either from an acceleration analysis. Okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 unknowns, 6 equations. Still, we need to find more equations. Okay, so luckily we have equations available from link number 4. So this one is actually easy. We only have one single rigid body, and this thing is not rotating. So you can easily write 2 equations there. Along the x direction, your F34x, that's going to generate your, assume that your A4 is horizontally. That's his M4 A4, right? Because your A4 can only, your link number 4 can only slide or horizontally. So there's no vertical component. So the y direction, you have F1 for y plus F3 for y. That is going to generate no acceleration because your slider cannot bump up and down. So that means the acceleration is 0. So the total mass is rho times point A by point 4 by point 4. This is the volume of the block 4. Okay, so A4, that's acceleration, which is A4 equals to d double dot, right? If you remember the problem description, the d double dot, or AD, actually equal to d double dot or equal to A4, whatever variables you're using. So this is the acceleration of this block. It has already been calculated from acceleration analysis. All right, so we have 2 more equations. How many unknowns we have here? We have 1, 2, and 3. Okay, so let's count all the equations. Remember that in this case, rotation gives us no equation, right? Because there's no torque in the system. All the forces are applied at the center of gravity. So that means no equations. So let's see. We have equation number 1, 2, 3, 4, 5, 6, 7, 8. We have 8 equations. How many unknowns? I'm going to use purple sign to circle out the unknowns. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have 12 unknowns, but we have 8 equations. So 12 minus 8, that means we still need 4 more equations. Otherwise, this problem cannot be solved. Where are these equations then? So we need to go back to the Newton's third law. So that means, for example, at joint A, let me use a slide 4 as an example. At joint A, F23x should be minus F32x, right? Because your joint A can only experience the same amount of force. So whatever force is generating is actually whatever force is receiving. So that's Newton's the third law. So we have F23x equal to F2332x. The same thing along y direction, we have F23y equal to minus F32y. And then that's around joint A. So around joint B, you also have F34x equal to minus F43x, F43y equals to minus F43y. F34y equals to minus F43y. So these are that's your number 12, 11, 10, and 9. Okay? So you have 12 equations, 12 unknowns. And then the good news is they're all linear equations. You can organize them in matrix format and then find all the unknowns. Okay, so that's how we do force analysis. You can check the MATLAB code. I posted online. That code is special. It's able to calculate the torque at all these theta 2 positions. In this case, we only calculate the torque input when your theta 2 is 0. But in the MATLAB code, it actually gives you entire the torque values for different theta too. So please make sure you check them out. You will definitely need these in your future projects and homeworks. Okay. So here I try to explain how to convert those 12 equations and unknowns into a matrix format. So it's very similar to previous velocity and acceleration analysis, but in this case we just have a lot of unknowns, actually 12 of them. So that means you're expecting 12 by 12 coefficient matrix and 12 by 1 column vector for unknowns. So first of all, you just organize all the unknowns in column vectors, and then you name the equation numbers from the top to the bottom, 1 to 12. And then the way you fill in the first row is you need to find the equation number 1, which is here. You need to find the coefficients of all these 12 unknowns and then fill in these coefficients. So in this case, we only have two terms for equation 1. So the coefficients for f1 for y and f3 for y are 1. All the other coefficients are 0. So you find all the f14, f34, which are f14 and f34y. So these two, they are 10 and 11th unknowns. Their coefficients are 1. All the rest of them are 0. So that's why you put 1, 1 for the 10th column and 11th column, and then all the others at 0. So on the right hand side, you have, so this is the equal sign. You fill in the constants on the right hand side of the equation. So in this case, it's all 0. So that's why you have 0. So let's focus on the second equation and fill in the coefficients in the right order. All right. So the second equation, first of all, we know M4A4. That's the constants on the right hand side. And then there is only one coefficient, which is F34x. Where's F34x? That's 12, 11, 10, and 9. So the ninth coefficient is 1. All the others are 0. So that's why you fill in the ninth one as 1 and all the others as 0s. Okay, so that's the second equation, which corresponds to the second row. So you can find the equation number 3. Number 3 is a little bit confused because you have to plug in the T23, T43 back in. But then, because in order to save the video time, I'm just going to provide you the solution. If you have any questions, you can ask me during the regular lecture hours.